Hello folks. In this video we are going to be introduced to the topic of buffers. This is our last topic of the unit. Our objective is that we can determine the components of a buffer, what makes a buffer, and also explain how a buffer works in resisting a change in pH. So the first thing is the definition of a buffer. So a buffer is an aqueous system that resists changes in pH. And it can do this by neutralizing an added acid or an added base. To do this, a buffer must contain two parts. A buffer must contain significant amounts of a weak acid and its conjugate base, or it has to contain significant amounts of a weak base and its conjugate acid. So over here in this diagram, this is forming a buffer, and I'm taking a solution of a weak acid and its conjugate base, and I'm pouring them together, and this is the buffer solution. So let's look at that example a little bit more in detail. So one example of a buffer is a solution that's made from a mixture of the weak acid. This is acetic acid. This is what we used in our titration the other day. And sodium acetate, its conjugate base. Okay? So a buffer is able to neutralize additional base and additional acid. So let's see what would happen if I add a base to this buffer. So which part of my buffer is going to be involved here? Well, if I need to neutralize a base, I need to use my acid. So with the addition of a base, the weak acid component of the buffer is going to react and neutralize that added base, forming water. So it is able to react with that excess base and produce water and neutralize that addition. When we add an acid, you want to think about what part of my buffer might help maintain a constant pH. Well, an acid would react with a base. So the addition of a strong acid like hydrochloric acid, HCl, will react with the conjugate base. Sorry, I had that sentence wrong. This should say the conjugate base neutralizes the added acid. The conjugate base neutralizes the added acid. And again, it's really not the sodium that's reacting here, it's really that conjugate base. So once again here, my buffer solution, my buffer solution has both my weak acid and this conjugate base in equal amounts. If I add strong acid or H3O+, my weak base is going to react with it, so that decreases in concentration and it produces a little bit of the weak acid. If I add my hydroxide, if I add a strong base to this solution, the conjugate acid or that weak acid is going to react with it, so that decreases and I'm producing more of this conjugate base. So that's why a buffer works so well, is because this buffer system is a cycle. I start with, again, my weak acid can neutralize strong base. This will produce conjugate base. So this produces a conjugate base out of the system. And then the conjugate base is able to neutralize strong acids, forming HA. So this can buffer as long as both components are present, because it's like a cycle. My weak acid neutralizes my hydroxide, producing conjugate base. Then my conjugate base can neutralize acid, producing my weak acid. And so a buffer regenerates itself in this process. However, if I add too much acid or too much base, it will the buffer wouldn't work because you would fully deplete part of that system. So you can only neutralize a little bit of each. So let's look at the equation that comes up with a buffer. This equation is called the Henderson-Hasselbalch equation. pH equals pKa plus log of A minus over HA, where the A minus stands for the concentration of conjugate base at equilibrium in the buffer, and HA is the concentration of weak acid at equilibrium in the buffer. And pKa equals negative log of Ka, remember. And I can also use pKa here to get Ka of my acid. So just a reminder of those switches that can happen, okay? All right, then we want to think about what makes a better buffer solution, okay? So one thing that helps is that if I have a higher concentration of the weak acid and conjugate base, the more that I have, the more acid and base I then can neutralize. If I have similar concentrations of a weak acid and conjugate base, that is also helpful. So we don't want to have a lot of one and not a lot of the other. And then the other thing is the pH of the buffer needs to be close to the pKa of the acid. So we have actually already seen a buffer solution before. We saw a buffer solution in our weak acid titration. So you might have noticed on your pH curve, it looked different than the strong acid and strong base. In the beginning, it has this buffer region. So in a weak titration, the buffering region will occur before equivalence point. That's when, again, you have both the weak acid, weak base, conjugate acid, and base present in solution. That is true if I have a weak acid being titrated or I have a weak base in the opposite direction. So it's the point before equivalence. And again, if you look back to what I showed you the other day, at this point B, this is where my solution is a buffer. I'm halfway to equivalence point, and really anywhere in this range is. Because in this titration, this was the point where I've added half of the amount of base required to neutralize the acid, producing conjugate base. So in this one, I have adequate amounts of both the weak acid and the conjugate base, and that is why it's a buffer. You need both of those things present. So let's look at a couple practice questions to test our knowledge of a buffer. So the first thing we have to do is be able to identify a buffer solution. So take a look which one of these solutions is a buffer. Okay, let's check it out. So solution A, is it a buffer? No. The reason is because this one has a weak acid and a strong acid. That's not going to be able to buffer. You need both a weak acid and its base. Let's look at the next one. So in this one, I have HNO3, and I do have its conjugate base. However, you need to recognize that HNO3 is a strong acid. That cannot buffer because this conjugate base has no power. The next one, HNO2, I have my weak acid, but do I have its conjugate base? I do not. The last solution then is my buffer. I have a weak acid and I have a salt that contains its conjugate base. So this is our buffer. All right, let's look at this one. A buffer contains equal amounts of a weak acid and its conjugate base and has a pH of 5.25. What would happen to the pH after an addition of a small amount of acid? So I have a pH, I'm adding a small amount of acid. So what's not going to happen is my pH isn't going to go up. It's not going to become more basic. I'm adding a little bit of acid. The buffer is going to be able to resist some change in pH, but it's going to change a little bit. So this 4.15 is too big of a change. A change in 1 pH, remember it's a log-based scale, that's actually becoming 10 times more acidic. Instead, 5.15 makes sense. We have a small change in pH, and it's slightly more acidic because as it neutralizes the strong acid, it produces a little more of its conjugate acid. The last question I want to look at is which equation shows how a buffer of NH3 and NH4Cl can neutralize a strong amount of strong base. So take a look, which one makes sense? Okay, so let's take a look. So NH3 and NH4 plus here. This one is my conjugate acid. This is a weak base. So when I think about what's going to neutralize my strong base, that will be my acid. Let's look at our choices then. Is choice A correct? Well, choice A is showing the neutralization of an acid, which is not correct. We want to see how it neutralizes a base. This next question shows a weak base reacting with a strong base. A base can't neutralize another base. Instead, part C shows the conjugate acid NH4 plus neutralizing the strong base, producing more of my conjugate base. So that's all for buffers. So I would check out section 17.1 to 17.3 in your textbook, kind of skim through those sections, and then in your reading guide, for now, you're just doing questions 1 through 3. Tomorrow, we will be focusing more on the math part of the buffers using the Henderson-Hasselbalch equation. Have a great day. Thanks for watching.